Hello everyone and welcome to Geeks for Geeks. The problem which we are going to see today is a program to check if a binary tree is a BST or not. By BST here we mean binary search tree. So let's look at what do we exactly mean by binary search tree. So binary search tree, also known as BST in short, is a node based binary tree which has basically these three properties. So the binary search tree satisfies these three properties. And now let's look at the all the properties one by one. So the first property says that the left subtree of a node contains only nodes with keys less than the node's key. So let us understand this with an example. So given a binary tree, so if we are starting from this node, so this condition says that the left subtree of the node contains only nodes with keys less than the node's key. So it means that the left subtree of this node will be this. So all the nodes in this subtree, the left subtree, should have the keys less than 4. So here the key 2, 1 and 3 are all less than 4. So this is the first condition for the binary search tree. Now the second condition is that the right subtree of the node contains only nodes with keys greater than the node's key. So this is basically the opposite of the previous condition. So when you are going left, you should have all the keys which are less than the node's key. When you're going right, so then you should all the keys of the right subtree should have the keys greater than the key of the current node. So as the right subtree has only one node here and it has the key 5, so 5 is greater than 4, so this also satisfies the condition. So now we are done with two conditions. Then comes the third condition, that both the left and right subtrees must also be binary search tree. So here we check the condition for the root. Now we have the two binary search tree, the left subtree and the right subtree. So the right subtree is definitely a binary search tree because it is just one node. But for the left subtree, again we need to check that yes, 2 is the current node, so 1 is less than 2 and 3 is greater than 2. So again this also satisfies the conditions of the binary search tree, and then we have the leaf nodes here. So these also are the binary search trees in itself. So this whole tree satisfies the condition to be a binary search tree. From the above properties, it's actually implied that each node, that is the item in the tree, has a distinct key. So because you need to have the condition that the left subtree should have values less than the current node's key, then right subtree should have the values greater than the current node's key. So it means that you cannot have duplicate values inside the binary search tree. All the elements have to be unique. Okay. So now let's look at the methods to check if it's a binary search tree or not. So we are gonna see multiple methods, and we are gonna improve basically on our way from method 1 to method 4. So following is a simple program. For each node, check if left node of it is smaller than the node and the right node of it is greater than the node. So here we are going to check the just the one node which is to the left or to the right. So this is the this is the basically the function. Uh, so here we are just checking if the node is equal to null, then we return true. That is 1 in this case. Okay. So then we have the three conditions here. We are checking the immediate left node that it should not be null. This is basically the sanity check. And then we check the data inside the left node with the data inside the current node. If the data in the left node is greater than the current node, then we return false, saying that it's not a binary search tree. Similarly, we have the second condition here where we are again doing the sanity check for the right node, that it should not be equal to null. And then we are checking that if it's not equal to null, then in that case, the data of the right node, if it is smaller than the data of the current node, then we are going to return false. That is 0 in this case. Then for the third condition, we are recursively calling the isBST function for the left subtree and the right subtree. If any of these calls returns as false, then we return false, saying that it's not a binary search tree. If after all these conditions, the program doesn't return true or false, 1 or 0, then we say that it's passing all the conditions, so it is basically a binary search tree. Now there is something wrong with this algorithm. Let's see. So if we are given this binary search tree, so it will compare 3 with 2 here. Yeah, 2 is smaller than 3, fine. It will then compare 3 with 5. Yeah, 5 is greater than 3. It's good. Now it will compare 1 with 2. 1 is smaller than 2. Then it will compare 4 with 2. So 2 is smaller than 4. So that is also fine. Then we have 1, 4 and 5 which are leaf nodes. So basically these are binary search tree. So our algorithm will say that this is a binary search tree. But you need to notice that the root node has the key 3 and a node in its left subtree has a key 4, which is not allowed. All the elements of the left subtree should have the keys less than the node's key. So this algorithm basically fails here. So we cannot basically rely on the immediate left or right child. So what's the correct solution? So let's look at a correct solution, which is not that efficient, but we'll get to that. So here for each node, instead of checking the immediate left or right child, we'll be checking if maximum value of the left subtree is smaller than that of the node, and the minimum value of the right subtree is greater than the node. So again, we have the code here. So we are doing the basic check that if node is null, then return true. Then we have our 3 conditions here. So let's start with the first condition. So again, these basic sanity check that if nodes left, uh, if the left node is not equal to null, then we are basically checking the maximum value of the left subtree with the current node. Similarly, we are again checking here uh, that if the right node exists, then the minimum value of the right subtree should be greater than the node's data. If it's the other way around, then we return false. After we are done with these two conditions, we basically recursively call the SBFT function for the left and right subtree. Now here we are assuming that minimum and maximum values will be calculated by this max value and min value function. Now this algorithm is basically correct, but there's an overhead with having to call these maximum value and min value functions. So okay, we'll discuss that later, but let's first try to execute this. So we start from here. We have the node 3. So we compare it with the maximum value of the left subtree. So the maximum value of this left subtree will be 4. We are comparing 4 with 3. 4 is greater than 3. So on the first iteration itself, we see that it's not a BST, and uh, this doesn't. This is basically free from the loopholes of the first algorithm. Now let's talk about why it is not efficient. Because it traverses over some parts of the tree many times. A better solution would be which looks at each node only once. So in this method 3, we are gonna use a utility function is BST util, which is gonna work from at the top to bottom approach. So it will have the values int min and int max, and these will be basically the minimum and maximum values that will be allowed. So initially these values will be int min and int max, and as we go from top to bottom, the minimum and maximum values will basically narrow down. The minimum maximum allowed values will narrow down. This will be more clear when we actually run through the code. So for the time being, let's see that this will be the basic structure is BST, and is this in this is BST function will be passing the root of the node, and then we'll be calling is BST util with the node and the minimum and maximum value. So for the first time, we are passing the minimum and maximum value here. For the other calls, will not be passing the minimum maximum value. Will actually be passing the values according to the node's actual value. So let's see. So this is the code here. So let's first concentrate on the isBFT function. So it gets the node here, root node. It calls isBFT util with the node int min and int max. Now this is the whole crux of the algorithm here. So you get the node, you get the minimum allowed value, you get the maximum allowed value. Now what this algorithm will do is that it will check that if the node's data is within the minimum and maximum value. If it's not, it will return false. If it is within the minimum and maximum value, then we'll recursively call this function for the subtrees or left and right subtree, and we'll also be tightening the minimum and maximum constraint. So for the left subtree, what we are going to do is we'll keep the minimum value as same as the previous call, I mean the current call in this case, but the maximum value will be nodes data minus 1. So this is the basically the maximum value which will be allowed. And since we cannot have duplicate values, so we're doing a minus 1 here. Now for the right subtree, we'll have the nodes data plus 1, again because we don't allow duplicate values, and then we have the same maximum value. So we are basically running this algorithm, and we are uh, going over the elements only once, and we are basically from the top to bottom we are just passing the constraint in which the elements should be there, and we are also achieving the all the three conditions of the binary search tree. So this is basically the driver function. So we have the int main, and we have here the method to create a new node. So this is basically the whole implementation. Now let's look at the time complexity. So the time complexity is order of n. It is very intuitive because we are just traversing over each element once. So the time complexity has to be order of n. And we are basically not storing anything in the order of n. So the time auxiliary space is also used as order of 1. Okay, now let's look at the method 4. This method doesn't come naturally to some people, but it's again a great solution, and that is using the in-order traversal. So what we do is we do the in-order traversal of the tree, binary tree, and we store the result in an array, and then check if the temporary array is sorted in ascending order. So by ascending order here, we mean that the array should be sorted from smallest element to the largest element. If it's sorted in ascending order, then it's a BFT, otherwise it's not. So the time complexity will be order of n, but in this case, we will have to have a auxiliary array which will take the space of order of n. Now we can also avoid the time and the space complexity of order of n by basically having the having an element previous which will keep track of the previously visited node, and we can actually check if the current node is greater than the previously visited node. If that is the case, then it's a BFT, otherwise it's not. So let's look at the code for it. So we are basically having a static variable here so that we can access the previous variable in different calls, and so we check if the root exists, Then we go to the right subtree first of all as per the in-order traversal. Uh, then because we are only allowing distinct values, so we check that the if previous is not equal to null, because in the first case the previous will be null. So we check if previous not equal to null, and roots data. So the current node's data should be if it's less than equal to previous node's data, then we return false because it should be greater than the previous node's data. Then we update the value of previous node, and then we call this function for the right subtree. If this condition doesn't return false, then we basically return true. So in total, we saw four methods. The first one was an incorrect solution. The second one was a correct solution, but it was inefficient because it was taking order of n square time complexity to do the job. The other two were correct and efficient, and including the algorithm where we were dealing with the in-order traversal. So both of these algorithms did the job in order of n time complexity, which is the minimum possible time complexity, because the size of the tree will be order of n, and you'll actually have to visit the each of the element at least once to work on that binary tree. So this is all for this video. Do visit this link. You can find all the material and the code used in this tutorial at this URL, and you can also use the ID there to get the first-hand view of how the program is running. Thank you.